This video is about the atmospheres of the planets. We're so concerned about the atmospheres of planets because of our bias for surface life. The atmospheres of terrestrial planets make up a very tiny fraction of the planet's mass. For example, Earth's atmosphere makes up less than 0.0001% of Earth's mass. We say that Earth is a water world, but the total amount of water on Earth in all its forms is only 0.023% of Earth's mass. Earth is primarily rock and iron. Even for the Jovian planets, their atmospheres make up a tiny fraction of the planet's mass. Our surface life bias makes us very interested in atmospheres. A planet's atmosphere helps shield a planet's surface from harsh radiation from the sun, and it moderates the amount of energy lost to space from the planet's interior for the Jovian planets, or from the planet's surface for the terrestrial planets. The crust of a terrestrial planet or moon prevents any of the effects of the atmosphere from penetrating into the interior of the planet. An atmosphere also makes it possible for liquid to exist on a planet's surface by supplying the pressure needed to keep the liquid from boiling away to space. Life on the surface of a planet or moon requires an atmosphere.
Before we look at the processes in an atmosphere, let's look at why some planets even have an atmosphere and others do not. If gas molecules move fast enough to escape a planet's gravity, the atmosphere will be thin or non-existent. That statement tells us the two things we need to explore here: the planets, or moons, gravity, and gas molecule speeds, which depends on the temperature of the gas. Let's start with the gravity part. How fast is fast enough? That is specified by the escape velocity, which is the initial velocity an object needs to escape a massive body's gravitational influence and never return. Focus your attention on the right-hand side of the picture. If you throw something up, it slows down as it rises and then falls back down. If you throw something up at a faster speed, it will rise to a higher height before falling back. If you throw something up from the surface of Earth at 11 kilometers per second, it would finally stop rising only after being infinitely far from Earth. That's Earth's escape velocity. Of course, if you throw something up faster than the escape velocity, it never stops rising. The left side of the picture shows that the escape velocity at different distances from the planet gets less for greater distances, which makes sense, since gravity gets weaker with greater distances. This is why atmospheres leak away from the top of the atmosphere. Molecules at the top of the atmosphere can escape more easily than those near the surface or closer to the core because the gravity is weaker at those greater distances from the planet's center. Temperature is a measure of the random motion energy of the particles in something. If a planet atmosphere is hot, the gas molecules move quickly. If the planet atmosphere is cold, the gas molecules move slowly. At a given temperature, the more massive gas molecules, such as carbon dioxide, nitrogen, and oxygen, move slower than the less massive gas molecules, such as hydrogen and helium. Therefore, less massive molecules can get to higher elevations above the planet or moon and more easily escape from the planet or moon. Atmospheres leak away from the top, leaving just the heavier molecules down closer to the planet or moon. So we have the competing effects of gravity and temperature. If you increase the gravity, the gas molecule will stick around close to the planet. If you increase the temperature, the gas molecule is more likely to escape into space. To determine which one wins, you have to do the calculation described in the Astronomy Notes textbook. There are other ways that a planet or a moon can lose its atmosphere besides this so-called thermal loss mechanism. I have a link to the section in the Astronomy Notes textbook that describes the effects of the magnetic field, solar wind, photodissociation, and large impacts. Impacts from asteroids and comets impart so much energy to the atmosphere's gas particles, they escape the planet's gravity. It's like a superheated, super rapid thermal loss. Solar wind blasting happens if the planet does not have a magnetic field. The solar wind chips away at the atmosphere particle by particle until the atmosphere is gone. An example of this was the loss of Mars's atmosphere. The thermal loss mechanism explains why the terrestrial planets in our solar system have thin atmospheres and the Jovian planets have thick atmospheres. The terrestrial planets lost on both counts. They have low escape velocity and are close to the sun, so they are hot or warm. The result is a thin or non-existent atmosphere. The Jovian planets won both counts. They have high escape velocity and are far from the sun, so they're much colder. Now, we have found Jovian exoplanets in other star systems that are really close to their star and still have enough gravity to hang on to their atmospheres.